Hello guys, hi professor, my name is Oscar Venegas. I come from Mexico, although I live in Sacramento, California. Currently, I'm working as a radar engineer in a startup based in Sacramento, California. I have lived in California since 2023. Before California, I lived 1 year in Denver. That is why I decided to start. I enrolled in Colorado State University for my master's degree. Very nice to meet you all, and let's start with the presentation. Um, the network that I chose to analyze is the internet topology as an autonomous system graph. So let's start. The description of the network. As I mentioned, I chose to analyze the internet topology as an autonomous system. So what does it represent? It is basically a snapshot of the internet as an autonomous system. So each node represents either an ISP, a large organization, or a network operator. For example, it can be AT&T, Comcast, Meta, Google, one of these big players. The type is undirected unweighted network. The scale, it is about 6,500 nodes and around 14,000 nodes. The data source, it was collected via the University of Oregon. Programming details and tools that I used. So from the resources that the professor provided us, I decided to use Graph Vs. No local setup was required, which means I didn't have to install anything on my computer. So all the analysis that I made was made online using GraphV's interactive pipeline. Core operation perform. Load and parse basically imported the network in H-list format. The visualization, apply a force-directed layout. The filtering, reduce the visual clutter using filters such as degree threshold and largest connected components. And finally, for the analytics, I use the inbuilt tool that GraphBees provides in order to visualize the network. These are part of the results. Hopefully you can see um, the network. It is a little tricky to visualize it, but on the left side I am presenting some results about some data about the network that I chose. As I mentioned, every single node represents a big organization or an ISP. So it is a network visualization. The picture is a layout of the graph, often force directed. So the center core, highly connected transit backbones, the outer low degree edges, autonomous systems, customer smaller networks, and the colors. What about the colors? So detected communities, modules, clusters, basically. It means uh, what I wanted to show is the structure, not the physical geography uh, of the nodes, right? So the overall size and sparsity. So this network has about 6,500 nodes, as I mentioned, about 13,000 edges, which sounds big, but the density is extremely low, about 0.0006. So it is a very sparse graph. Most possible connections do not exist. So how dominated the structure? Even though the average degree is only 3, the maximum degree is about 1.5 thousand. So the gap tells us the network is highly skewed. A few nodes act as a major hubs, while most of the nodes have only a handful of connections. So disassociative mixing. The assortativity is negative. minus 0.18, meaning high degree nodes tend to connect to low degree nodes rather than other hubs. That's typically of a hub and spoke systems like influencer nodes, router topologies, or star-like collaboration patterns. Local clustering and triangles. We see, it is a little tricky to see, but it is about 20,000 triangles on an average clustering coefficient of 0.25. So there is a meaningful local community structure. Neighborhoods of a node often connect to each other, but the fraction of closed triangles is 0.0096. So the visual interpretation is something that I would like to mention. That's exactly what the picture shows: a dense central core, the color cluster, plus a huge number of peripheral nodes radiating outward. Many of those are likely connected through one or a few other hubs. Um, Regarding the results, the graph interpretation is core periphery structure, dense central core. As I mentioned, it has multiple big hubs of major transit. Most probably they are ISPs with many peripheral low degree autonomous system at the edges. It is a hub-dominated connectivity. A few high-degree nodes act as a backbone hubs, while most nodes have only a few links. Community modular patterns. Coloring by community, typical reverse cluster driven by geography and peering routing policies. The routing implication: hubs and high betweenness nodes are critical. Um, let's go to the next slide. Okay, the results and interpretation is basically a visualization limit, computational cost, and scalability. This autonomous system level topology shows a clear core periphery structure. A dense core of major transit ISPs sits at the center, while many low degrees autonomous systems appear at the edges, as I mentioned. So the key routing takeaway is that high betweenness hubs are critical points of failure. Target removal of few cores hub can fragment the network far more than removing many random peripheral nodes, which means basically that if we remove one of these big huge hubs, then it's critical for the infrastructure, for all the small hubs and end users. The question that is in my mind, so it's basically: how resilient is the internet graph to target attacks on the top hub highest betweenness autonomous system compared to random failures? So basically, what will happen if we remove one of these big huge hubs? So will the network will be able to manage this big failure? So nowadays there are multiple tools which use AI orchestration and stuff like that. So most of these tools, they handle these type of failures as isolated failures, which means they are not a very high impacted failures. But when there is a big issue, the human hand or the engineering team has to take the control of this. So there is no, as my knowledge, there is no tool in charge of the orchestration which can handle this level of failure. Finally, these are the references that I used. Hopefully this was a very useful presentation. It was a very useful presentation, at least for me. So hopefully you can know, hopefully my explanation was clear and you can know a little bit more about me, about the online students. So thank you very much for your attention, and bye.